All right, cool. Let's dig into chapter 8, which is encryption. Let's see what we're doing here. So in this lecture, we're going to talk about the absolute basics of encryption, right? And it's actually a pretty important part of cybersecurity, although it's more of a capability that just kind of exists, less than being as overt as some of the things we've already talked about in the class. But if you've heard of ransomware, encryption is what is at the heart of causing the problems within ransomware. We're going to talk about modern cryptography, like basically how how encryption works at a very high level, because it's basically all math at this point. We'll talk about what cryptography is appropriate for your organization. Basically, we'll talk about where you would use different types of encryption algorithms and types of encryption for appropriate situations. And we'll briefly talk about VPNs, but it's really all about encryption. Like basically, when you're done with this lecture, you should be able to have a high-level understanding of exactly what encryption is in the space of technology. All right, so encryption. Encryption is basically taking information, right? Data, a message, an email, just raw, zeros and ones on the wire, and making it unreadable, indecipherable, except it has to go through a process and be decrypted, right? And the trick is that only the people that you want to know the message get it decrypted, right? So think about it this way, right? So like back in medieval times, Roman Empire, etc. They didn't have the internet, they didn't have text messaging, they didn't have encryption, certainly. So if I needed to get a message to one of my allies or my armies at the front line or something like that, attack at dawn, like you're trying to coordinate a multi pronged attack, right? Attack at dawn, attack at dawn, attack at dawn. You're telling 3 different armies, we're all going to converge on our adversary at dawn. Well, you got to get that message to them, right? So if you give it to a scout and the scout gets intercepted by your adversary, the adversary has the message attack at dawn. So then the adversary packs up all their stuff in the middle of the night and leaves, or they attack in the middle of the night, right? You get it. The value is that the message is only accessible to those that you want it to, right? This is confidentiality. This is what we talk about all the time. Okay, so that's the heart of it. Encryption is basically that. Now, just to keep it relevant for today's day and age, ransomware is basically using encryption, the same technique that we use for good purposes, to by a threat actor to encrypt a victim's computer or files or network or whatever, and they don't give the key unless you pay them the ransom, right? So again, they're using the same technology to keep all your data protected from you unless you pay for it, right? So that's why it's nasty business. Okay, so it is very, very relevant in the world of cybersecurity, as I mentioned. I've been working in this field 17 years. Like, I don't do like heavy math or anything like that. Like literally, you just kind of pick a solution. You make sure that the solutions that you buy are using encryption that is at a level that is unbreakable for current technology, and you move forward. You're not really getting into like the actual crypto. All right. So the basics, again, decryption's the reverse of encryption, right? So that they're two sides of the same coin. The way that it currently works in modern day with the mathematical crypto is that you give it a message, you use some algorithm to jumble up all of the information in a way that, because of the algorithm you use, it's understood how to reverse that technique, okay? So, yeah, it's very difficult to recreate the message without the key. One of the really interesting things is the algorithms are all public knowledge, open source, if you will. And that makes them actually stronger, because if they were weak, it would get discovered by the public. The trick and the real important part of any encryption is the key. And the key is what changes for each different version of encryption. So here's something that is a core thing that you really should take away from this lecture. There's 2 types. That's it. There's 2 types of encryption. You can have a million different algorithms. You can do it this way and that. But there's only 2 types of encryption techniques. There's symmetrical key and asymmetrical key, all right? That's probably going to be on the quiz. Very simple to remember. Let's start with symmetric key because it's quite obvious. Symmetric key is symmetrical. It means that the key that party A uses and the key that party B uses is the same key, right? So if you've ever, encrypted a zip file or encrypted a Excel file, right, or password protected it so the person can't open it without the password, right? PDF does this sometimes. That is symmetric key. You type in a password and then you send the file or whatever it is to the recipient and you send them the key. Hopefully you send it in a different medium, right? So you email them the file and you text them the key, right? If you just email them the key, if the email gets compromised, putting it in a separate email is not really secure in any way. So that's symmetric key encryption. Now, asymmetric key encryption is heavy duty and it's asymmetrical because it has public and private keys. And the way that this works is when you generate a public key and a private key, and then you, like Jerry, or you, organization, the Citadel, you have the public and private key. The names are quite intuitive, right? You put the public key out in the public space, you put it in your email, you put it wherever you want, you attach it to your swipe badge. Your public key is public for anyone to get access to. Your private key is for you only, to be kept private, and in fact, if it gets out, it's kind of like your password. If it gets out, you need to revoke the key and issue a new public key because now that private key can't be trusted. And the way it works, we'll get into a bit of the detail here. I'm not going to go super deep on the math, but the public and private key actually have a mathematical relationship based on kind of a formula that gets used. And that's how they get tied together. Again, we'll go into examples in detail on how this works. The symmetric one is really easy for people to wrap their head around because I have a key. It's like a key to your house, right? Like it unlocks the door. So you put the door lock everywhere. And then if you want someone else to be able to open it, you give them the same key. The asymmetric one is a bit trickier to wrap your head around. And like I said, we'll go into some specific details. But generally the idea is that you use if you're going to send me a message, you encrypt it with my public key because only my private key can decrypt that message. That's the relationship between the public and private key. If you encrypt the message, the email, with my public key, and someone could use my public key to decrypt it, that would basically be symmetric key encryption, which does no good because, again, my public key is everywhere. So the deal is, you encrypt with your public key, only I can decrypt it, which means for a fact that I'm the only one who was able to read the message, right? So you can have confidence. Even if it falls into our adversary's hands, they capture the scout who's trying to deliver the message to our army. They can't do anything with the message because the encryption algorithm is so strong and they don't have the private key to decrypt it, so it's useless. Right? You can do some other fun stuff with public-private key that I'll get into in a little bit, but basically that's the gist of those two. All right, so let's take a trip down memory lane, y'all. I kind of gave you an example with the scout and trying to coordinate in the war. So Caesar is kind of credited, although, it was happening before, but one great example of the first kind of cipher was the Caesar cipher. Now, the Caesar cipher is very, very simple, and it's basically... take the alphabet A. Hold on one second. Can I do this right? So take the alphabet, right? Line it up A through Z. Then you take the alphabet again, A through Z, but you shift it some number, right? So let's say it shifts 1. Caesar cipher value 1. So A now becomes B, right? B becomes A, right? So we shift it over. So B becomes A, C becomes D. And then at the end, because it rotates around, Z becomes A. So you'll see here in the example, a dog is the message, right? Keeping it super simple for the purposes of class. A dog. If we shift it 1 over, the A becomes a B, the D becomes an E, right? What comes after O? P, right? So everything shifted 1, so O becomes P. Now, if you want to get a little more clever, shift it 2. So A shifts 2, it becomes a C. B shifts 2, B becomes D, right? So you can see that basically BEPH and CFQI are essentially, it's not encrypted, but it's like encoded secret message. And the idea is that you would have to know what the number was for the cipher to be broken. I mean, this is really super basic, right? I mean, basically, if you think about it, any message you get, you have 1 in 26. You just have to do it 26 different times before the message would just pop out, even if you didn't know what the shift number is. This is super insecure, obviously. This can be broken in minutes and a bunch of other things. But it is a nice basic introduction to the concept of kind of encoding messages. So if you intercept this message and it says CFQI, you're like, what do I do with this? Like, unless you knew that this thing was encoded in some capacity and you started looking for it. So let's get a little bit more tricky. After the, this is why the Caesar cipher stinks, right? Okay, so it's easy enough to guess the thing. Frequency distribution is also a thing. So like in the message, if we shift 1, right, every A becomes a B. So if if the secret message was in Aardvark, 8 llamas, right? Just to be silly, but to have a bunch of A's in there, there'd be a ton of B's in that sentence, right? So you can kind of like look at it and be like, I don't know. Like if you've ever watched Wheel of Fortune, RSTLNE are like the 5 letters that everybody picks, that to the point now where they just give them to them. But it's because those are some of the most highly frequented letters in any word in the English language. So if you see a bunch of a certain letter in an encoded message, you can kind of assume like, well, it's not a Q, it's probably like an R or an S or an E, and you can kind of puzzle it out and then get the message, okay? So it's a monoalphabetic cipher, meaning that there's only one alphabet, right? You got the actual message and then the second message that encodes on. Some other, historical ones. This is really just for like, to understand where we came from, because literally everything is mathematical encryption at this point. We don't do any of this other stuff, but at bash, well, a railfence. Here, let me show you a couple different ones because they're visually more interesting than me talking about it, but let me do this. All right, so check it out. An at-bash cipher is basically kind of like the Caesar cipher, except instead of shifting right or left, they basically just flip the alphabet around. Again, monoalphabetic, ridiculously simple to break, no big deal. All right, let's check out the rail cipher, railfence cipher. This one's kind of silly. This is like something that children would make up, I swear to God, but it gives you the right idea. So with the rail, here, can I zoom in on you? With the railfence cipher, the way that this one works is, basically the message is we are discovered, run at once, right? So this is a secret message to get out, like the jig is up. Oh, it's right here. We are discovered. Now, the key here, the key is really the number, right? The key is the number, and that's the number of rails. So in this case, we have 3, so you can see how there's 3 rows, and then you basically write it on this like oscillating, V kind of shape, almost like a sine wave. And then once you do that, you kind of stack them down, and you can, meaning they drop down, and you can see that this, hold on one second. You can see that this message here is now, this is the encoded message, right? So if you were to intercept this, you might not understand that the jig has been up and they're going to flee the scene, right? So it's all about that key. Again, this is not even encoded, like the actual letters are here of what the secret message is, so you can kind of puzzle it out at that time. What else was in there? Veneer cipher. This is another one that's kind of visually really interesting. it's got like, it's basically like a huge table. Okay, so this is a Vignere cipher. Now, this one, it's important to have this whole table up. You'll notice that across the top is A through Z, and down the left is A through Z. Again, it's all about the key. So the key is, in this case, isn't going to be a number like the railway cipher. It's going to be a word. So like, let's just say the word is cat. Cat is going to be the keyword, and then like whatever the message is. So, you know, like whatever, attack at dawn. So you would basically start with C, right? Can you see right? Hopefully you can see this, right? My little cursor. You start at C and you go down to A. Like, so you're going to basically have your message here, but you're going to look it up, iterating over the word cat as like which column you're going to dig through, right? So just, I know it sounds confusing, but bear with me, right? So attack. So A is the first letter, C for cat. So the first letter of the encoded message is C. Now, the second letter in attack is T, and the second letter in cat is A. So then we come down here. And so now T is the second letter, so our encoded message is CT. Now, T is the next letter in cat, so we go over here, and T is the third letter in our message that we want to encode. So we come all the way down here, and there is M. So now our encoded message is CTM. Now, because cat is only 3 letters, we'd start over with cat. So we start here at C again, and ATTA. So again, C. So now our encoded message is whatever. It's a CTMC, right? So you get it, right? That's basically how a Vignere cipher works. And then you can use, you know, like basically if you know the key, like anyone can have access to this grid right here. Like everyone, this is public knowledge, this grid. So then having the key is the key to decoding the message, right? So you could send someone a decoded message. They would also have access to the Vignere cipher thing, and all you have to do is tell them the key through a different medium, right? So maybe you send the message with one scout and you send the key with another scout, or you've already worked out a key that like you guys, like, you know, hey, I always share messages with you and we always use the key cyber, right? Like always. Obviously there is some risk if the key gets popped, like in any other case. All the messages can be decrypted, even historical ones that have been captured, right? So that's kind of the problem with that. Another, what else? Oh, the Enigma. So let's spend a minute talking about Enigma, because this is where it really gets awesome. So Enigma was basically the code machine that Nazi Germany used in World War II. And this thing, like, it's not quite mathematical, but we're getting much, much closer. So check this thing out. Hold on one second. Can I do a full screen on this? So this baby right here, you would plug in to these like down here is kind of like you'd have to wire it up a certain way. Then you'd have to turn these dials to specific numbers, and that was part of the key, right? So how you wired it and what 3 numbers you chose was the key. And then you would type the message on this keyboard, right? So you can see the letters are here, right? So, you know, it's basically the common keyboard layout. So I would type in my message, attack at dawn. But when I press A, up here, something would light up, and I would write that glyph down as like my first letter of my encoded message, and then so on and so forth, rinse and repeat. So kind of similar to the other ones, except this thing, multiple issues, right? 1, you had to have an Enigma machine. 2, you had to know how to program it for the specific message, right? So Nazi Germany was using the Enigma all over the place, but like, you know, maybe for like communications that went into Berlin, you would have this this kind of configuration for the Enigma machine, or messages that were coming from Berlin would have this configuration, or every month the configuration would change, et cetera, et cetera. Anyways, super, super effective. The Allied forces really had no clue what was going on until in England, Alan Turing, who's famous in computer science circles, him and his group at the think tank there, were able to crack the Enigma code. They got a couple of these machines. They had some messages. They kind of used math. They backed into it. Once they broke Enigma, then they could use the machine to decrypt all the communications that were coming in and out of Germany. It was arguably one of the most pivotal points in turning the World War II from an Axis winning situation into an ultimately allied winning situation. So really, really huge. And this is like, we're right on the cusp of starting to use math at this point. So that's our history lesson. Oh, let's do a little bit more, right? You can get a little bit trickier by using multi-alphabetic instead of mono-alphabetic, which is what Caesar cipher was. So let's just do Caesar cipher times 2, right? So you shift it 1, then you take the encoded message and you shift it again some number, right? Same thing, but in reality, it's still like it's easy for computers to break, right? Like you can just kind of work through it. But some of that frequency analysis now changes, right? Because if an E, which is super frequent, gets changed to a Z, then you got a bunch of Z's in there, and then you move that over to well, actually, I guess the frequency analysis would still work, actually, to pop out where the E's were in that case. But you get the idea. They're trying to get a little bit more clever. So now let's talk about how modern encryption works, okay? I'm going to do my best to communicate this. Just know that I don't expect you to have a computer science degree. I don't expect you to be able to count in binary and stuff like that. But just stay with me, okay? This is gonna make sense in a second. This is a very simple explanation. So we as humans count to 10. 1, 2, 3, 4, like base 10 is what it's called, base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, right? And we increment the second digit space, and then we 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, increment the second one. We all know how to count to 10, right? By tens. So that's how humans have kind of built our number system. Well, computers use base 2. We use base 10. Computers use base 2 or base 16, which is just a condensed version of base 2, but I digress. So base 2 is called Boolean logic or binary. And it's basically zeros and ones. If you've ever heard computers talk in zeros and ones, like that's what we're talking about. This is basic computer science stuff, but we speak in zeros and ones, and there's a reason why. Now, when you're converting messages into data, they're zeros and ones. That's what computers see as files and stuff like that. So when we're doing transfers on the zeros and ones, that's how we're encrypting them. And we got to keep track of how we're doing it, okay? So we're going to talk about 3 different binary math operations, right? So we talk about adding it, subtracting in the base 10. Well, with binary, you get some extra functionality. You can use logical operators. So there's 3 we're going to talk about: and, or, and exclusive or. And is what you would think. Looking at this number, 1101 and 1001, and this is kind of the sum of the and function being applied to it, okay? So and means that both the first digit and the second digit, because you're going to use two numbers, 2 digits, they are both true, right? So also zeros are false, 1 is true, okay? So it's saying that they're both 1. They're both true. So you can see in this simple example, 1 and 1, they're both 1, so it's true, returns 1, true. 1 and 0, they're not both 1, so the result is 0 or false. 0 and 0, they are both the same, but neither of them are 1, so neither are true, so they're 0, they're false. This one can get a little tricky because you think that they're the same, so it should be true, but it's not. And then 1 and 1, since they're both 1, then they're 1, okay? Or operations. Now, or means either of them are 1. That's basically what that means. 1 or 1. Well, since one of them's 1, it's true, 1. 1 or 0. As you can imagine, one of them's a 1, so it's a 1. 0 or 0. Since neither of them are 1, it resolves to 0. False, right? False or false. True or false, it's true. one and one, or excuse me, one or one, true or true, then true. Okay. Hopefully this makes sense. Exclusive OR. Now, exclusive OR is special because exclusive OR means that they are not, they're not the same, basically. One is true and one is false. So, one or exclusively OR, like basically they're kind of like, they're different, right? Exclusively. So, one or exclusively or one. Now, this was true for and, this was true for or, because, you know, one and one is, or true and true is true, true or true is true, but exclusive or true exclusively or true is false, because they're not exclusive of each other. Now, one exclusive or 0 is true, and this is really the only situation where exclusive or is going to resolve to 1. And 0 exclusive 0 is 0, false exclusively or false, right? 1, 1, no, 0. Now, what makes this so powerful is because if you, like, stay with me, if you take the solution, right, the output of this operation, and reverse it back up using exclusive OR, watch what happens. 0 exclusive OR 1 is 1, right? 1 exclusive OR 0 is 1. 0 exclusive OR 0 is 0, and 0 exclusive OR 1 is 1. Do you see how you can go backwards through the function? This is like the crux of modern cryptography and encryption, because you can back out and get the original message. So almost think of it, this is our message, this is our key, this is our encoded message, and because of the mathematical properties, we're able to convert from encrypted or encoded to decoded, right? Using this operation. That's the takeaway. All right. So let's kind of highlight how you would do that. Now, I'm not going to have you go buck wild on this, but just understand, ASCII text is a way to map a character, like a letter, to a number, and it's like universally recognized. Like, you know, like, just, I don't know how to explain it here. Give me a second. Okay, so hopefully you can see this. You see how, like, basically every element that you could possibly, you know, type or have in a computer has some ASCII numerical value, right? So the space bar is a you know, decimal 32 or a hex 20. You could see, like, character A is 65. Now go back over here to our message. Character A is 65. So basically this is just a conversion. There's no mystery here. We're just converting this into numbers. Then we convert the numbers into binary. Now this is a 8-bit number, 01000001. This right here, if you were to convert this from base 2, which is what it is, to base 10, it would be 65. So, like, essentially this right here and this right here are identical. There's a mapping there, okay? If someone wants me to go into, like, how you count in binary, we can do that. Just let me know. But it's you don't need to know it for the class, okay? So now that we've got this binary message right here, right? This right here says a dog in binary. So now let's use exclusive OR. And this is our key right here. It's a lot like what we just did before, except now it's like on turbo. 0 exclusive OR 1 is 1. 1 exclusive 1 is 0. 0 exclusive 1 is 1. I invite you to pause the video and rip through this. It should make sense. But here's the point. This is our ciphertext down here. If I hand this to you and you try to map it back into ASCII, map it back into letters through the mappings, this will turn into a message that doesn't make any sense. And the problem is you need this key to map it back into its original text. Okay, so these are the terms. I've been kind of throwing these terms around, but let's formally define them. The key is kind of the value that is agreed upon as the secret. Okay, like that's the key. It's appropriately named. Plain text is the original message. Clear text, sometimes people call it. Ciphertext is the encrypted message. And the algorithm is the method for what you are doing on it. So this exclusive OR is it's an algorithm, right? It's super basic. It's super, super simple. What we're going to do, or what we're not going to do it, but what the cryptographers do is they use many different forms of these Boolean operations and complicated math formulas and apply it between the plain text and the ciphertext to get, between the plain text and the key to get the ciphertext, okay? We're just going to talk about a couple encryption methods. This is more like so you recognize the word or you hear it. I don't expect you to study or do any of this on your own, okay? So Blowfish is a symmetric key encryption algorithm. No big deal. You use the same key back and forth. But, basically the power of symmetric key is that it's easy to share the key. And then if someone gets the encrypted text, this is the level of difficulty it is to break it, basically. DES, this was the standard for quite a while, used by the government. It is no longer. You can see there's some information here about what it is. The message is broken up into blocks. Then they transpose the blocks, and off you go. Do some math functions on it. Now AES is the current standard of which it's considered unbreakable, right? We like AES 256 when we can. Basically, this is considered the standard unbreakable encryption right now. So when we buy solutions or we're talking about do you do like data at rest encryption and stuff like that, AES 256 is what we're requiring, basically, right? You can do different key sizes, but obviously the bigger the key, the more secure it is. Okay, so let's talk about, I've been talking about symmetric key and asymmetric key, but let's talk about what's the problem with symmetric key? Well, the main problem I've already highlighted is that if anyone gets the key, then anyone with the key can open whatever the message is. So if I send you the message and it's intercepted, you can still read it. Well, like if a copy's made, right? You log into my email and make a copy or whatever. So now you can read it, I can read it, adversary can read it. That's not good. They can also read older messages. They can read newer messages. It's just you can't guarantee who got it and who read it and everything like that, right? So the answer to how to handle that is public key encryption, right? So, well, I guess the slide here is saying how do you transmit the symmetric key? So that's another whole problem. Unless we get on the phone and agree to it. But like I showed in modern encryption and stuff like that, you're not going to be able to tell someone the key over the phone. It has to be communicated almost computer to computer. And how do you protect that? How do you not have a man in the middle attack? How do you have any assurances that it's actually encrypted? So the answer is PKI, or public key infrastructure, or public key encryption. It's used for a lot more than just passing symmetric keys, but this is how you do it. Okay. I've already explained this at the beginning of the class, what public and private keys are used for. So I'm not going to spend any time on the slide. Okay, so again, this thing relies on prime numbers. It's crazy math. It's like a beautiful mind type stuff with formulas flying by your head and everything like that. I can't even pretend to understand what they're doing. I just understand how to use it. PGP is a free one that a lot of people can use, and you can Google it if you want, but you can basically use PGP to generate your own public-private key pairing and make your public key available on, in your email signature block or headers and stuff like that. I did that for a while, but the reality is I'm not communicating with anyone about anything sensitive enough that would warrant that level of encryption. So I don't use it anymore. Okay, yeah, some more on PGP, no big deal. Here's what it looks like if you want to go download it for yourself. I'm sure this says version 658. I'm sure it's way further along now. So this next couple slides is basically explaining a little bit behind the math of how public key encryption works. So I'm just going to kind of run through it, right? You get two large prime numbers, prime meaning that they're only divisible by themselves, and 1, right? So they're not a multiple of some other number. You take those two numbers, you multiply them together to get another number, then you do some math to get, like, so n equals the two prime numbers times each other. Then you got another letter m variable, and you multiply, the prime number minus 1 and the other prime number minus 1, and then you get some value m, right? You see how this is turning into like a spaghetti incident here? So now you pick another number e that's a coprime to m, and it's got to be smaller. So you do all this math. I hope you understand that it's incredibly complicated based on a prime number. But at some point you get the key. The key is generated by this math function. And because, again, they're prime numbers, or they're mathematically bound to each other, that the system works for encrypting and decrypting based on the public and the private key. So here's the deal. You get this public key E, right? Or publish E and N. Whoops. E and N is the public key, and you keep D and N as the secret or private key. Okay. So let me see if I got any slides around this. You can use, this is RSA, like if you're interested on like how this algorithm works and all this stuff, they're kind of the leaders in this space. But, I wouldn't unless you're really, really into math, I wouldn't go too deep in this thing here. So before I get into this slide, I just want to tell you some other use cases of public key encryption. Again, I've got my secret private key. The world's got my public key. So the obvious use case is you write a secret message, you use my public key to encrypt it, and you send it to me, and only my private key can decrypt it. We talked about that earlier. The other approach is you send me a message and you encrypt it with your private key, right? It's encrypted with your private key. Now, hopefully you understand that would mean that only the public key could decrypt it, which means if you send me a message using your private key as the encryption, I don't get to see your private key or anything like that, but anyone can use your public key to decrypt it. Now, why would you want to do that? The thing is, because only you have a private key, I know for a fact that message is actually written by you. Excuse me, because no one else could have encrypted it with the private key. And if you really want to get fancy pants, you can encrypt it with your private key, then take that encrypted message, encrypt it with my public key, and send it to me. Then I use my private key to decrypt it, and then use your public key to decrypt the decrypted message. And now only I saw it, and I know that only you wrote it, right? So there's attribution there. This is like definitely getting crazy, but that's another way to do it. You can also like people do that kind of non-repudiation thing where you use your private key to sign something and your public key proves it. Oftentimes with email communications, like can you imagine if a message came out from like a military commander, you would definitely, like launch the nuke. Like you sure would want to verify that message did in fact come from the source who was authorized to make that command. So that's another use case for it. So you will see in deeper crypto circles, people making all sorts of claims that their crypto is unbreakable. In my experience, I've seen people, I don't know why they do this, but people who are like developers, they will write their own crypto. And it's not really crypto. It's closer to like the Caesar cipher text things where like they're like, oh, no one knows how I do it. It's super secure. No one will be able to break it. And in fact, it actually gets broken because they're not experienced cryptographers with advanced math degrees. So you see stuff like that all the time. Basically, stick to AES. That's your best bet. Okay. So yeah, these are bad cryptos. Kirchhoff's principle is basically kind of a tenet of modern encryption and stuff, and it's something I've said a couple times in this lecture already. Basically, Kirchhoff's principle says that the strength of a system is only based on the strength of the key. Like the actual algorithm and how it all works and everything can fall into your hands of your adversary, and it's not a big deal. It's if the key is, can't be broken or duplicated or simulated or anything like that, right? So that's kind of the gist of how good your crypto is. So digital signatures, this is exactly what I just told you a minute ago. I forgot the slide was here. So basically it's proving who you are by using your private key to sign things. No big deal. All right, so hashing is another form of cryptography, right? It's less encryption because hashing is one way. But what's cool about hashing is, if I can pull up a terminal here, I'll have to forgive my SimplyCyber stuff. Okay, so with hashing, you can basically fingerprint a file. Like you see this all the time in the virus world. Remember I told you like signature-based antivirus scanners are kind of trash because you can change what the signature is of a malicious file. Well, this is basically what signature-based AV does, right? So I'm just going to create a fake text file called CSC227, right? So MD5 is a hashing algorithm, and I do that, right? So this right here is the hash of this file. So if I got a piece of malware and I ran MD5 on it and I put this little fingerprint here and I upload that to all the antivirus scanners in the world using my product and they see this signature, then it is unequivocally the same piece of malware. This is how signature-based AV scanners work. And obviously why it has a problem, because you can, can I echo hello into CSC227 text, right? So now I just edited that file, CSC227. I added the word hello to it. So when you run MD5 again, it's a different file, right? It's a completely different file. And you can see that the hashing algorithm is, or the value of the hash function is different. So if I sent you this file, right? If I sent you this file and I said, hey, check out the CSC227 text file. By the way, the hash is this. If anybody manipulates the file in any way before it gets to you, you can use the MD5 hashing in this function or whatever hashing algorithm we agree on to validate the integrity of the file before you read it, right? So if I sent you this message, it says attack at dawn, and I tell you this hashing algorithm, and then you get the message, and the message actually says, surrender to our enemies. We're losing the war, and it's time to give up. Two different messages, right? And then you look at that hashing algorithm, and you're like, well, it's definitely, the integrity is compromised. And by the way, we should figure out how this message got intercepted and modified en route because we got a problem. Maybe we got a mole in our ranks or something like that. But that's what hashing is, and that's how you'd use it, basically. Okay? And by the way, they pointed out on the slide here, but the chances of two hashes having the same value are like incredibly astronomically unlikely. So there's no amount of like tweaking and modifying and touching the new edited file that says surrender to generate that same hash. Like you would never be able to do it, right? So that's the power of the hash. It doesn't encrypt anything though, right? Like the message isn't changed. It's still plain text. Here's a couple different hashing algorithms if you want. So a rainbow table. So with some of these complicated, passwords, well, I guess I should have told you this too. Like when you are sending over, when you authenticate into an environment, right? You type in your username and password and it sends it to the server to authenticate, like in Active Directory, which is pretty popular across the globe. It doesn't actually send your password over. Like, so it'll actually, my password, right? It'll actually hash your password. Well, hold on. Let me my password .txt, whatever, like whatever. Just pretend that CSC227.txt is my password, right? So it would take the quick hash of my password and then send this over, right? And then obviously the server on the other end has my password and it knows the hashing algorithm, so it computes the same hash and verifies if they're the same hash. That means that I sent the same password, they have the same password, it grants me access. Okay, well, it's pretty intensive, resource intensive to calculate those hashes when you're trying to do it. So these have these things called rainbow tables, which are basically pre-calculated hashes on things. So you'll see, like when you're trying to brute force a password or something like that, you know, you can use these rainbow tables because it takes time, it takes computational power to calculate all these things. But if you already have a table that has all of them, like imagine a table that had every single possible permutation of every character that you could type on a keyboard. They don't exist, right? Because like that's just there's billions and billions of options, right? But if you had every single one and you had calculated the hash on every single one, then if you could intercept a hash on a network, it could take you seconds to look it up in the rainbow table, and then you back into what is the password. Because again, hashing is one way. You can't unhash a hash to get the original plain text that was hashed. You can only do it one way. So if you have the hash table lookup, you can look up and get what the password was. Okay, so that's what a rainbow table is. Okay, so how do you make hashing tougher? You can do things like adding random bits of information. So I type in my password 1234, and then the salt is like 5678 or whatever. And because it's hashing and sending it over, and then the receiver is doing the same hashing, it knows to add that salt. So it makes the rainbow table difficult, because if you do have a match in the rainbow table, it's actually going to translate to not what the actual true value was that was hashed initially, because that salt has been added, okay? Okay, here's just an example of what salting looks like, right? So here's the password, pass001. Here's what it looks like in binary. Then you add a little bit of salt. And I guess it's basically, they're getting a little bit tricky here by inserting a bit every fourth bit, right? So 01110, 01110, 01110. So you see this extra bit, it's going to screw everything up. And then when you convert it back, you get this thing, which is most certainly not my password. So steganography, I won't spend a lot of time on this because we actually have a cool lab that we're going to do with steganography. Look forward to that. But basically, it's like hiding a message in an image, right? So they have some historical steganography. Again, we talked about different ways to hide stuff. I think the most interesting one is the second bullet, where they shave a guy's head. They tattoo a message, or they write it, probably tattoo it. They write a message on the skin, let the hair grow back, and now it's kind of like hidden until they get to where they're going. They shave their head again, and off they're running. So super cool, but I was going to say modern steganography, but we're still in the historical steganography. Invisible ink, microdots on images, you know, like where you got like the monocle or whatever, the microscope, and you're looking at the messages that are hidden. All sorts of cloak and dagger stuff. It's really, really cool. It makes great movies, great spy movies and stuff like that. But let's talk about what can be done today. As far as terms go, payload is the actual message being hidden. The carrier is like the vehicle that the message is being hidden, and the channel is like whatever the medium is that's being used, right? So in the lab, we're going to use a text file with a secret message in it, and we're going to hide it in an image file, which is really cool, which means I could post the image on Instagram, Twitter. I could use a special hashtag like hashtag CSC227. So any image I show the CSC227 hashtag, you know that that's the one you can pull down and pull out the secret message, right? So it's, and by the way, it's not like you can look at the picture and notice any difference. Again, you'll see it in the lab. It's pretty cool. Okay. So ciphertext, well, cryptanalysis, like how do people break crypto? It blows my mind that people can do this, but you can just study, if you intercept a message, you can study the message and see if you can identify like frequency analysis or, you know, some like the structure of it or anything, right? Maybe compare it to other messages. Maybe I know in World War II in the Pacific Theater, they were actually able to intercept a bunch of Japan's messages, and they weren't fully able to break it, but they were able to understand that like certain words were code names for certain islands. So, like send 600 oranges to Wake Island, right? Well, they're not sending 600 oranges. They're actually sending like 300 tanks or whatever. So, at that point, you don't have the whole message, but the Allied forces in this case were actually radio in like false information about like, oh, hey, this is like on public channel that they knew would get intercepted, and say like, hey, we're going to be sending 30 battle cruisers to Pearl Harbor this week. And then they would like wait, intercept the messages because Japan didn't know they had access yet, intercept the messages. And then they would say like, oh, the enemy is sending whatever, 30 baskets to grandma's house. And like, okay, so baskets is battle cruisers, check. And grandma's house is Pearl Harbor, check. Okay, so then when you see those words come up again, you already have decoded them basically. All right, so the known plain text attack is basically you have the known plain text and you have the encrypted text of some capacity, and you're trying to figure out like what's the algorithm, what's the key, so you can break it, and then if it's symmetric key, then you got the key and you can decrypt other things. Chosen plain text is another cryptanalysis technique where you have access to the kind of the algorithm to encrypt, and you can put in information that and you can see what the output is, and you can't you can kind of use that information to help figure out how it works and maybe what the key is. That way, if you can start to see patterns and stuff like that, then if you get actual communications that are intercepted and stuff like that, you can apply what you know to reasonably analyze whatever the actual messages are. A related key attack is where the analyst has access to multiple keys and is able to run the unknown, like pick random text and run them through against the key and see what the outcome is against multiple keys to see if they can discover like what type of relationship the encryption or the algorithm, has with each other. Again, so you can kind of figure out how this machine system works, and then be able to ultimately translate or intercept and decipher or decrypt whatever the communications are that you're trying to get access to. Okay, so in summary, hopefully, like I promised, you have a basic understanding of crypto and encryption and public key encryption versus symmetric encryption or asymmetric and symmetric encryption, asymmetric being the one that uses PKI. But basically, we use encryption all the time for protecting the confidentiality and ensuring the integrity of data. Bad guys use encryption all the time to encrypt everybody's files and then charge a ransom in order to decrypt them. Encryption is a standard piece of cybersecurity. We use it all the time. We use it to secure our backups. We use it to secure sensitive information like healthcare information or credit card information, financial stuff like that. We use it to have encrypted HTTPS on the internet, right? Like all web traffic is HTTPS. The S stands for security. The security is enforced by the TLS protocol, which is basically establishing a secure tunnel across. One thing I didn't mention that's worth noting is that asymmetric encryption has a heavy processing burden on it, right? Because you might ask, why would we ever use symmetric encryption if asymmetric is so strong and so awesome? Asymmetric has a cost of a computational burden on it. Symmetrical is way less intensive, but it's lighter weight, it's easier to break. So what the modern internet does, when you establish an internet connection that's secure, what happens first is, obviously you do the three-way handshake to do TCP, right? So you can have a secure, a high integrity, stateful connection to the server. But then you translate an asymmetric key, or really the server sends you asymmetric key. You use that key to encrypt a symmetric key that is then sent back to the server. Then the server has the symmetric key. Then you drop the asymmetric thing and you use just the symmetric key communication for that internet session, right? So we use the asymmetric one to assure that nobody gets the key of the symmetric key except the two parties that want to be involved in this communication. And then we use the symmetric key to have a lighter weight and faster processing and transmission of the information. Okay, so that's another important bit there. Hope you enjoyed it. I know this was a little bit of a more of a complex and a little bit shorter too, but hopefully you had a good time, and I'll see you in the next lecture.